Welcome back, Chemistry 30. This is the EQ1.2, the equilibrium constant section. The objectives here: write the equilibrium constant expression for any reaction and calculate the value of the equilibrium constant when given the equilibrium concentrations of the reactants and products. So last section we looked at what equilibrium was, what chemical equilibrium was. Remember, it's a dynamic process. There's constant movement, and reactants and products at equilibrium are constant, and the rates of forward and reverse reaction are equal. So a reaction in which reactants convert to products and products go to reactants. So we have reactants going to products, and then products going back to reactants, and of course we symbolize those together as a double half arrow. Reactants going to products, products going back to reactants. In the same vessel, if it's sealed, naturally leads to chemical equilibrium, regardless of how complicated the reaction is. And of course it has to be reversible, such as when gases are together. And of course, when equilibrium, constant amount of reactants and products, and then forward and reverse rates are equal. So constant amount, equal rates. So if we look at this example here with ammonia, this is a common one. It's called the Haber process, which is critical for the production of fertilizers and therefore critical for the world's food supply. In the Haber process, nitrogen gas and hydrogen gas react in high pressure and temperature in the presence of a catalyst to make ammonia. In a closed system, however, the reaction does not lead to complete consumption of nitrogen and hydrogen. So in previous years in science classes, we'd have said, well, reactants come together to make products, and those reactants are used up. Well, because this is a reversible reaction, some of the ammonia goes back and makes nitrogen and hydrogen. At some point in the reaction, so in the closed system, however, the reaction does not lead to consumption of that and that. At some point, the reaction appears to stop with all three components being present at the same time. Now, let's take a look at this. So here we have, so we're starting off with hydrogen and nitrogen. So hydrogen, nitrogen, and of course ammonia. So it makes sense. We don't have any ammonia. So this is concentration versus time. So concentration, just think about that as being the amount we have. So the amount of ammonia at the start, nothing. We simply have nitrogen and hydrogen. But nitrogen and hydrogen, when they combine together, they get used up, used up, used up. As they get used up, they're making more and more ammonia. And then eventually we get constant concentrations. And we saw a graph like this in the previous section, EQ1.1. So of course, the flat lines or plateaus come to be about right here. So we would say the equilibrium is achieved right here when these become constant. If I had started off with ammonia, just ammonia in a system, it would break down and make nitrogen and hydrogen until, of course, we would reach constant again. Now look at this, H2, NH3, N2, H2, NH3, N2. It doesn't seem to matter what you start off with because you have the same results here. So see in the above graphs, it does not matter initially what you have because the equilibrium concentrations become constant no matter what. And the amount of concentrations look very similar relative to each other. So if you look at the next page, there's a relationship between the concentration of reactants and products at equilibrium. Suppose we have this, a general relationship in which we're comparing reactants to products. So big A, big B represents the chemical species. So what type of reactant and product do we have? And little a, little b, little d represent how many. So they're the coefficients in the equation. Okay? So if we look here, what we're doing is we're calculating products to reactants. And really what we're doing here is we're figuring out the probability. So let's just say that. Really calculating the probability of products compared to reactants. Okay, and the coefficients here become exponents. So it'd be like if this d was a 3, I'd have d to the 3, or d times d times d. The probability of d times d times d. So if you recall in math class, that's how probabilities are calculated. So this is called the equilibrium constant expression for the reaction. It is a quantitative, so a number way of describing the equilibrium of a particular reaction. The constant, which is called K subscript EQ, is called the equilibrium constant. And sometimes it's symbolized as Kc, where it's the concentration. Concentration constant. If we have things in terms of molar concentrations, which we do a lot of the time. The numerator, so the top of the equilibrium expression represents the product side. And each raised to a power equal to its coefficient in the balanced chemical equation. And of course the denominator represents the reactant side. I'm not sure why I didn't highlight that initially or bold it. And this is really easy. So if you look at the Haber process, if I was looking at writing down the K equilibrium expression, or Kc, used interchangeably, it's products over reactants. So products, so NH3, and we use square brackets to indicate molar concentration. And 2, so the coefficient becomes the exponent, because really it means I have two NH3s, NH3 times NH3, because it's a probability, over reactants. N2, there it is. H2, there it is, but I have 3 of them. So H2 times H2 times H2. So there we go. All right, pause the video maybe and see if you can write down the equilibrium expressions for these scenarios. Okay, so pause it, and then we'll come back and talk. Okay, hopefully you had a chance to try those. So I'll just try it here on the next page. That's where I have room. So for the first one, I'll call it Kc, call it whatever. So the products, O2 to the 3, over O3 to the 2. Products over reactants. And then the coefficients become exponents. Gas, gas, gas. Notice these are all gas forms. AQ, we have that on the bottom. B, I'll call it KEQ this time because it doesn't matter. The product side is NOCl, so square brackets, to the 2, all over NO squared multiplied by Cl2. So again, probabilities. Because really what this is, it's the same thing as simply writing NOCl times NOCl, see, taken twice, over NOCl2. So we usually just use the exponents to simplify that. C, KC, AG, NH3, 2 to the positive, multiplied by Ag plus and NH3 all squared. That's it. That's all there is to it. So keep on trucking here. Maybe try to pause the video again and try these ones. Okay, if you had a chance to do those, So the first one, KEQ, product HI squared all over H2 times I2. H2 times I2. Easy. B, I'll call it KC. Doesn't matter again. The product CDBR4 to the 2 negative all over CD2 plus BR minus to the 4th. It's not too bad. Just remember it's products over reactants, right hand side over left hand side, and the exponents are equivalent to the coefficients in the original equation. Okay, one final part before we jump into the assignment. The value of Kc can be determined if the equilibrium concentrations are known. So each of these square brackets here imply equilibrium concentrations. So if you take a look at this example here, so if we have this scenario, N2O4 in equilibrium with NO2, of course products of reactants, NO2 squared over N2O4. So we can have various experiments in which we have initial amounts of N2O4 and NO2 in a container, and then time passes and we get equilibrium numbers. So notice we start off with different scenarios, 0.02, 0.03, so different amounts of each. And if we were to look at this, and it doesn't matter which one we pick, but remember, it's the equilibrium concentration. So we would pick this and this, NO2 over N2O4. So pick those, and that's what was done here. 0.0172 squared over top of the amount of N2O4, 0.0014. I would get 0.21 as an answer. If I did the same thing with these equilibrium concentrations, or these ones, notice I get the same Kc or KEQ value. So what that leads us is that we are using equilibrium concentrations here to figure out KEQ to determine Kc or KEQ. The value of that number, as we'll see, depends only on the particular reaction and on the temperature. So we'll see that temperature kind of makes changes later on, and not on the initial concentrations, because as we saw here, it doesn't really matter what we start off with. It's the equilibrium concentrations that we use, and they give us our values. The value of Kc is the same for each experiment, even though initial concentrations were different. And then lastly, we don't have to worry about a unit because each reaction will have a different unit depending upon what the KEQ looks like, how many reactants and products we have there. So no units, since different units are used, etc. All right, you should be able to do the EQ 1.2 assignment, and we'll see you again.